So, let us go for some more advanced examples on parallel program writing in CUDA, and here we will pick on some mathematical entity called Julia sets. So, what is a Julia set? It is named after French mathematician Gaston Julia, who worked on complex dynamics during the early 20th century. Now, J represents a set of points contained in the boundary of a certain class of functions defined over complex numbers, and we define this kind of sets as follows: that you are given a set of points in complex plane. A set J can be constructed by evaluating for each point a simple iterative equation which is given by this. So, J n is iteratively computed using the previous value of J n being squared plus a constant complex constant C being added, and if a point does not belong to Julia set, then it would provide a behavior that is in iterative application of the equation will yield a diverging sequence of numbers for that point. So, essentially what will happen is for certain specific complex certain specific points on the complex plane, if I continuously iterate over that equation, it will I will get a sequence that is diverging. Then I will say that that point does not belong to J, and otherwise if I get a sequence which is not diverging, I will say that yes, this point is part of the Julia set. Now, of course, for you can understand that this computation is very much a function of what is my choice of this complex constant. For different choices of complex constants, I would be getting different Julia sets. So, I mean just again, I mean how do we represent complex numbers in CPUs? So, I mean you can have a structure complex with variables r and I. I mean they are float variables, and they represent the real and the imaginary part, and I can have several different operations, for example computing the magnitude and doing an addition and also doing some basic multiplication. So, if I look at doing an addition, I am expecting two complex numbers are provided, and I am going to write back the result of the addition by using a pointer to a complex type structure raise. So, it is as simple as this, and again I can do a multiplication in the complex plane using standard mathematical formulas like this. So, as you can see that I have been provided with complex typed input A, complex typed input B, and I am computing this results of the multiplication in terms of the real part and the imaginary part separately. So, this first equation will evaluate the real part and the second equation will evaluate the imaginary part, and once this is done, I have the result written back in this by using this pointer raise, right. So, the first thing our program will do is it will try to make a mapping from the pixel grid to the complex plane. Of course, we are trying to do, our objective here is we will also like to write the GPU code to compute a Julia set and represent those values as a bitmap on the screen. That will kind of create a very nice looking pattern. So, for doing that, the screen is represented by a pixel grid, and I have to map each point from the screen, its coordinate from the xy location to a corresponding AB location, right. So, this is how I have the xy coordinates starting from this corner, and here I am going to compute the corresponding AB. So, first thing we will do is we will do for computing these AB points for the given xy points, I do a scaling. Before that scaling, I subtract from this x a dimension by 2, and that gives me a value here with respect to the origin, and also if I do a subtraction over the y, that also gives me a value in terms of b, and I do a further division by dimension by 2 to do a scaling. So, when I say that I have a corresponding value in terms of AB, and I will be doing some computation on this, and then I will determine whether this value is whether this coordinate is a member of the Julia set or not. The fact that it is a member will be represented by a different color. So, the color coding we are going to follow here is that color xy color xj yj, if it is red, that would mean that it belongs to the set, and if it is black, that means it doesn't belong to the set. So overall, I would expect at the end that there is a blackened screen, and on which I have a red colored pattern, which is representing the Julia set. Now, how would the Julia function look like for a specific point? I mean, when I am doing a CPU side computation and I am trying to evaluate whether a specific point on the screen is a member of the Julia set or not. So, you assume that you are supplied with the xy coordinates, that is the coordinates with respect to the corner here. The first thing you are going to do is you are going to do this transformation in terms of scaling, and you are trying to find out what is the corresponding AB values of the coordinate. Of course, dim represents the dimension, that means the total size here of the screen size that I am considering, and I am also considering that it's a square sized area or dime cross dime. So, using this transformation that we have discussed here in terms of aj and bj, we now create this variable indices jx and jy, right. So, when I have these jx and jy created, I use them to now denote the new coordinates here in terms instead of this x and y's. So, this essentially will give me a result of applying this formula here, right. So, essentially I will be doing all my Julia set computation on this jx and jy, and it is very standard. So, just to look at the original mathematical formula, all we are supposed to do is we are supposed to iterate over this equation multiple times, see what are the results, whether the result is converging or not, and based on that we take a decision whether it is a member of the Julia set or not. And of course, there is this complex constant parameter which we assume is provided to us. So, here for our purpose, this complex parameter is assumed to have a real part this and an imaginary part as given here. And so, we consider that the input value has a real part, that is jx, and the input value has an imaginary part, that is jy, and then we are inside this loop which is iterating 200 times, and it is basically executing this equation a times a plus c, getting recomputed and recomputed. So, for doing that, since a is of the type complex, and we carry out this function multiply, that is you multiply a and a, write back the result in R1, and then you take the content of R1 and you add it to C, and then you return it to R2, and then you check whether the magnitude is greater than some specific given value or not. If it is really so, then you return back, you say that the item is not in the set, otherwise you say that yes, indeed the item is a member of the set. The way you say that it is a member of the set is you write back this value of R2 here, and you also go back to the computation here. So, at the end what will happen is, if inside this 200 number of iterations it is never the case that the magnitude is crossing this 1000, then I have the final value here in A, and it is and if the loop executes up to these 200 iterations, never returning back here, then you finally make a return from this point, and you have the final value that is computed stored in the complex data type A. Now, so this is a code that is trying to design a membership decision for a provided x comma y value, right. That would be the summary here. You are given the x comma y value, from that you are trying to create a corresponding complex number A, you evaluate this equation, you see whether it's diverging or not. If you your definition of divergence here is that okay, I will execute this loop 200 times. If even after that this magnitude doesn't cross 1000, then I will simply return back assuming that yes, this is a member of the Julia set. corresponding to, of course, this choice of complex parameter C here. Now, of course, that's a membership decision function and it has to be called. So, for that I have a driver code which is here in terms of the kernel. So, essentially I am thinking that okay, for the entire input bitmap, that's representing the entire screen area, I am going to do a pixel by pixel membership testing for whether that any specific pixel is a member of the Julia set or not. That's my target. So, for that I set up this nice cascade of loops. Each loop is iterating from 0 to dimension, because of course I am going to cover the entire screen here. So, coming back here, I have this cascade of loops from 0 to dimension, and inside this cascade what I do is, first I make a computation of this offset. That means what is the location I am interested in. Offset is of course x plus y times the dimension. Why that is required, we will come into that, but before that we compute the Julia value. That means I pass these parameters x and y to this membership testing function Julia that we have discussed earlier, and in return backs and tell me that yes, this xy value is indeed a member of this this xy parameter value is indeed a member of Julia set or not. So, that is available here. So, if it is really a member, then Julia value would get a value 1, right. Now, if it gets a value 1, then we have this corresponding location. So, that means the offset times 4 plus 0 is being provided with 255, is being assigned the value 255, right. Now, why do I have this offset getting multiplied by 4? Essentially we are thinking that in standard bitmaps, a 32-bit pixel color bitmap is being represented by a 2D grid of pixel values, and each pixel has got its color being represented in terms of 4 channels. So, each channel is for red, green, blue and alpha, where alpha represents the transparency, and each channel's value is to be inside this range of 0 to 255. So, I mean with suitable combination of these values, I can generate the corresponding color. So, since I have to give for any pixel value, I have to give the corresponding values of these channels. This is how we are doing it. First, we are thinking that this PTR array is representing the bitmap. We do the offset computation to traverse to the corresponding location in the PTR. So, offset is nothing but x plus y times the dimension. So, essentially I can think that this offset represents one cell here. Now, the value in this cell, I mean it's of course each cell has got 4 channels. So, you have the multiply by 4, and after that you have to give the corresponding value for each cell, right. So, that is why you have 4 values plus 0, plus 1, plus 2 and plus 3. As we have decided earlier that if it is a member, then we are going to give a color it with red, and otherwise it is all black. If I have to color it with red, what we do is Julia value is 1 in the first channel represents red. So, I multiply 1 with 255 and write in the red channel. For the other G and B channels, we anyway keep them at 0, and we also have the transparency value to full. So, this is the kernel code for CPU, which is going to take each of the PTRs, that means each pixel position, and transform and tell me back whether this is going to be really inside a member of Julia set or not, and if it is a member of the Julia set, then it is going to paint that pixel position by itself. So, this is the kernel code in terms of the CPU. Now, of course, that code needs to be called. For that we will have a main function in C, where we first do the bitmap setup by using these functions. I mean, so this is a basic bitmap setup which will return the CPU bitmap, and we get the pointer that this pointer which is going to point to the screen locations. Now, of course, in this context we leave out the details of how bitmap data is constructed, since the primary focus here is that we are trying to see that how to do some computation on the bitmaps. Of course, getting bitmaps and with using suitable the suitable headers and all that is very simple. There are standard programs, and we'll of course provide you the references right here for that. So here we get the pointer to this different bitmap for the screen. We call the kernel with these pointer locations for each of them, and we finally do a display and exit here. Now, how about doing this computation for the GPU side of the program? Now again, I would like to say that this kernel call, as has been demonstrated here, is only for one location here, right? But how does it work? Because the call has been made, as you can see, for the base position, right? This CPU side code makes the kernel call for the base position, and then from that means I am passing kind of this location in PTR, right? And then I have these two outer loops which are going to traverse through the entire grid of locations and do the color this coloring part, and before that it is going to do the membership testing by using this Julia function. So this, as you can see, that just like for matrix multiplication, I had a cascade of loops first. The cascade of loops, the outer cascade of two loops were there to choose the row for the matrix 1 and the column for the matrix 2, and then the inner loop was doing the computation. So in a similar structure, I have these outer two cascade of loops which are traversing over these bitmaps, and the inner code is actually doing the Julia set computation and then deciding whether it's a member of the Julia set, and then correspondingly coloring up with a suitable value, whether it's red or black. So the overall idea is very simple, that since we are assuming that the CPU is single threaded, so there is a one thread of computation that's going to hover over this multiple outside cascade loops, and in each iteration of the inner loop it is going to do the Julia set computation and coloring business. Now what about the corresponding code in the GPU? So again we will have assumption that we have some device functions here. Now if you remember, for in terms of GPU kernels we made a classification. There is a device function as well as a global function. So the global function is a kernel that can be called from a host side code, and a device function is a GPU kernel which can be called from some other function that is already executing in the GPU, right? So just for your remembrance, let's just traverse back to this function declarations. So here we had device type function which execute on device, and they are callable only from device side functions, whereas we have global functions which execute on device but they are callable from host side functions. So here, as you can see, we define some device side functions. So one for magnitude, one for addition, one for structure. Now these are just like our earlier programs, which were basically the C programs which represented doing this computation in the complex plane in terms of magnitude, addition and multiplication. So they are just very similar here. Because they are like standard C functions, there is no hint of parallelism or anything here. We also have another device function which is named Julia. Now this is the function that is going to do the computation, that is the membership of the Julia set, and that's also quite similar. As you can see, that you do the computation of the positions on the with respect to the shift of origin and scale first with respect to Jx and Jy, and then you use those values to initialize a complex data type A. You make your simple choice of this complex constant values with respect to both the imaginary and real parts here, and you define these different types of complex types. We are just calling them CU complex because the CUDA equivalent part, right? And so you have this complex constant C which has been defined, and you have the input A, you have this original loop here. This just like the normal C code. Essentially you are doing the multiplication, then the addition, and then you are doing the magnitude testing whether it's converging or not. And if you are able to execute this code 200 times without ever returning out, then you say that okay, this is going to be a member of the Julia set. So this is just like the normal CPU side code, but then the question is, why do I start saying that yes, it's a GPU side code? The reason is, this is a device side function which will execute on the GPU, and it will be called from some other GPU kernel. So now let's look at the other GPU kernel. So this is it. So this is a global function. That means this is the GPU kernel which is going to be launched from some host side code. What does the GPU kernel do? The GPU kernel first identifies the x and y values. So that is essentially it can find out based on the block ID and the block ID x.x, then block ID x.y's, right? Now to get an idea that how is this block defined, let's go further to the host program. So this is the host program. As you can see in the main, I have that CPU bitmap, that function like earlier, which is providing me the bitmap definition, and then I do a CUDA malloc on the GPU side memory. On the GPU side memory, I am trying to transfer the bitmap, and then I design a grid here of type dimension 3, and then in this grid definition, as you can see, when the kernel is called with this block and number of threads per block as 1. So what is a block here? The block is just containing this dimension, comma dimension, number of blocks, right? So essentially that would mean for each position I just have a block ID and block ID x and block ID y, and every block has got just one thread. So that is why with comma I have a 1 here. These things will become more clear as we progress with the course. And then we have a CUDA memcopy command. Once the kernel has executed, we can assume that all the set computations have been done, and accordingly the bitmap has been painted, and then the bitmap display function is called, and after that we have a CUDA free for the device bitmap. So coming back here, we have this CUDA kernel whom I have provided with this many number of threads, 1 thread per block, and the number of blocks we have defined is dimension square, right? So using the block ID, I am getting a direct map to the pixel. I hope that is clear. So we go back to this nice picture here. So essentially now we are saying that we are launching these many threads as is the number of pixels, and I am also saying that we are launching these many blocks. That means essentially we are saying that we are launching these many blocks with only 1 thread per block. So once that launch is being done, every x comma y value of course will get the corresponding block ID x.x and the block ID x.y, and using them I first do the computation of offset. That's nothing but I have the x axis plus the y value, that's the number of rows that would be getting multiplied by the dimension of the grid. Now the dimension of the grid has been set as you can see, the dimension of the grid is set as the original DIM dimension value that we have discussed earlier in that graphic slide. So now for each thread in this kernel, I have got the idea that this thread has to decide for the Julia set membership position of one x comma y coordinate, right? So for that, this Julia function will now be called, and this Julia function is just like the original Julia function for the C code, is just the GPU equivalent one, but it's a device function, which means that this is already a kernel. This kernel has been launched with dimension times dimension, that means a number of threads, where each thread is supposed to look up to the membership of one element, right, one pixel. So since this is already a kernel and it is going to launch a C code which will do the membership testing. That is why this Julia function is now being called a function which is a device side function. So, it has got this device keyword tagged with it. So, once being passed with the parameters x and y, it should return back the Julia value, and just like earlier we will be using these Julia values to assign the corresponding suitable RGB channels here to these PTR memory locations. And with that, when this kernel's execution finishes, we have got the bitmap colored properly with respect to the Julia set computation, and finally the bitmap display image is able to display it properly. So, again, where does it get different in terms of the CUDA program and the original CPU side program? Like we have discussed earlier, the original CPU side program had this cascade of loops, but now when we start talking about this Julia set computation, we just do not have this cascade of loops. Instead of that, we have this kernel launch, and the kernel is launching that many dimension times dimension number of threads, and those number of threads essentially are executing parallel in the GPU, and while executing parallel in the GPU, each of the threads is responsible for doing a membership decision for each position here, and for each position it is doing the it is calling the device function Julia, and if the call is call returns to a 1, then it is doing a proper coloring of the bitmap here. Of course, it is 1, then it is writing the red channel, and otherwise it is writing 0 here, and so everything is black. With all that, when this code is executed, the host program finishes, we will get a nice pattern here. Now, as we have said earlier, that what pattern you get is also a function of what is the coefficient that you choose. That this was our choice of coefficient, as that we made for the complex constant C. For that coefficient choice, you would get this kind of a pattern. Now, this part of the code I would like to mention that this has been adapted from an introduction to general purpose GPU programming by Sanders et al., and we used that reference to write these programs, execute them in our environment, and reproduce this picture. So, this we thought would be a nice example after matrix multiplication. In both the examples, we are trying to show you how iterative job that the CPU does by having multiple hierarchies of loops can be replaced by suitable kernel launches, where you launch that many number of threads, and each thread does some specific job on some specific data element. None of these codes are optimized with respect to the GPU's architectural features, but all it does is it exploits the parallelism on based on the job at hand. First, we had the matrix multiplication program. As we discussed, there is a lot of parallelism because I can compute each of the matrix entities in parallel. Similarly, in the Julia fractal case, I am trying to take a membership decision about each of the pixels in the display, and that also can be done in parallel. And we thought this would be a nice example because this is also an example of a graphics program through which you are trying to see that how GPU acceleration can provide you good real-time graphics performance. Although we are going to deal more about general purpose graphics processing units, but graphics programs were the first workloads that were identified for graphics processing units. So, with that we would like to end this lecture, and thank you.